The program you are about to see depends on accurate color reproduction in the receiver you are watching. The test patterns we will show you will help you adjust your receiver as necessary. First, if this receiver has an automatic color correction circuit, turn it off. It may be labeled ACC for automatic color correction, AFT for automatic fine-tuning, or some similar name. Second, adjust the brightness and contrast controls so that you can see a white bar on the left side, a black bar on the right side, and 6 different shades of gray in between. Third, adjust the color level or color intensity control so that each bar is brightly colored but does not appear to glow or smear into adjacent bars. Fourth, adjust the hue control so the colors you see on the screen match the color labels we have provided. Finally, if these people appear to have normal skin tone, your job is done. If they look slightly green or blue, make a small adjustment to the hue control. Repeat this part of the tape if necessary until you are satisfied that this receiver is properly adjusted.
And we're getting a picture on the TV. It's one small step for man, one giant leap for mankind.
Television, a communication medium that allows the sight and hearing of millions to be focused on a single event as it happens, even across 250,000 miles of space. Today we take television for granted, yet the way TV works is probably less understood by most people than is space travel. Let's take a look at that technology. In the program on monochrome television concepts, you saw how a television picture is created by an electron beam scanning a phosphor-coated screen. You saw how the beam scans all the odd-numbered lines, then begins again and scans all the even-numbered lines. You learned that each complete set of odd-numbered lines is called a field. Each complete set of even lines is also called a field. The two fields interlaced together make a complete frame or picture. As the beam scans the phosphor coating, it causes the phosphor to glow with a brightness proportional to the varying intensity of the beam at each point. Together, all these thousands of glowing phosphor points recreate the original picture. You also learned that the scan of the beam in the picture tube is locked to the beam scan in the camera by synchronizing pulses. Using a waveform monitor, you saw that these synchronizing pulse tips were 40 IRE units below the zero blanking line. That the black picture level, sometimes called setup, is at the 7.5 IRE unit level on a standard signal. And that 100% picture brightness, or white, is represented as 100 IRE units. Finally, you learned that to transmit all this information requires a 6 megahertz bandwidth, with a little more than 4 megahertz assigned to the video signal. Now we make the transition from monochrome to color. Any complete understanding of how color television works must begin with the peculiarities of the human eye. Light signals are picked up in our eyes by sensory receptors on the retina called rods and cones. The rods are mainly concerned with peripheral vision and vision in low light levels. When watching television, however, the rods play a lesser part. So let's concentrate on the cones. Different cones are sensitive to different kinds of light. Those which are centered in the primary focus area of the eye, called the fovea, are sensitive to sharp detail, but not to color. Conversely, the rods outside the fovea are more color sensitive, but cannot distinguish a lot of detail. So, our basic fine detail vision can be thought of as monochrome, or black and white. Now, to that detailed picture, our eyes add color in large and medium-sized areas, but with less resolution. Now, what do we mean by large and medium-sized areas? And what about the small areas? Well, we have reasonably good color perception when we're looking at figures 1/5 inch or larger 10 feet away. If you're watching this picture at a normal viewing distance, you should be able to see individual stripes of red, blue, and green. But for smaller figures, between 1/5 and 1/20 inch at 10 feet, our color vision falls off dramatically. We can still differentiate color detail in hues of red-orange, but in all other colors, we tend to see masses of tinted gray rather than individual color details. And in very tiny areas, smaller than 1/20 inch at 10 feet, we cannot distinguish any color detail at all, not even in the red-orange hues. Oh, the lines are still there, all right. You just can't see them. It's one of the tricks our eyes play with light. As you probably know, light is a form of electromagnetic radiation and thus falls in the spectrum along with radio waves, infrared, X-rays, gamma rays, microwaves, and dozens of others, each defined by its wavelength, its place on the spectrum. Our eyes are sensitive to the portion of that spectrum we naturally call visible light. It extends from a wavelength of about 700 nanometers, which our eyes see as a deep red, to a deep blue at the high end, about 400 nanometers. The study of color and colored lights is called colorimetry, and we'll give you a brief primer to help you understand how color television manipulates them as a picture. The first thing any student of color learns is that there's nothing simple about it, and there are very few fundamental truths. What color is all about is largely a matter of who's defining it. For example, blue can extend anywhere in the spectrum from about 450 nanometers up to 400 nanometers. All wavelengths in between look like blue to the average observer, yet different people will choose different wavelengths to be their blue depending on their particular needs. Thus, in this program, we'll deal more with ranges of color when developing the concepts. Where we define specific colors, we'll do so with respect to a specific organization or purpose. This is a standard chromaticity chart established by the International Color Commission, the CIE, around 1937. Notice the presence of the visible light spectrum around the horseshoe, from a deep red at about 700 nanometers, around to the upper range of our vision at about 400 nanometers, a deep blue. But color has two properties, hue and saturation. When we talk about hue, we simply mean which color it is, blue, yellow, maybe puce. But saturation is a little more difficult. It means how much color there is. Let's back up a bit. The central area of our chromaticity chart is an area we see as white. Actually, there are an infinite number of whites in this area. All of them are made by combining all the other hues in slightly different proportions. Conversely, around the perimeter of the horseshoe are found pure hues, hues of a single pure wavelength. Now, if we were to draw a line from some pure hue on the rim to a point in the center area that we'll define as white, we could say that as we move along that line from the edge to the center, that once pure hue becomes more and more diluted by white. In essence, this is the principle of saturation. Any hue on the horseshoe itself is said to be 100% saturated. As it moves toward and becomes diluted by white, it becomes less and less saturated. Now we can define saturation as the amount of pure color when mixed with white, or if you prefer, the amount it's been diluted by white. It's also important for you to know that saturation is not the same as brightness. You may recall from the Monochrome program that brightness is the amount of light as measured in IRE units. A gray at 80 IRE units is obviously brighter than a gray at only 40 IRE units. Now let's add color. Here's a nice green. And just like the gray, The green at 80 IRE units is obviously brighter than the green at only 40 IRE units. But the proportions of green and white in both are the same. In this case, they're both 50% saturated. On a waveform monitor, the brightness is shown as the average value of the band in IRE units, while saturation is shown as the peak-to-peak value of the band and is given as a percent. Finally, here is the same green, both at 60 IRE units of brightness, but the one on the left is twice as saturated as the one on the right. In fact, the right one is so unsaturated or diluted by white that the green is barely detectable. So the distinction between brightness, or the amount of light in IRE units, and saturation, or the proportion of color to white in percent, is one to remember. Now, in looking around your everyday world, rarely, if ever, will you see pure 100% saturated hues. So it's pointless to try to recreate all pure hues for television. TV designers did, however, want to get as broad a mix as possible, consistent with real life. So they chose 3 hues that, when mixed, would recreate almost any color visible to the average person. They chose this specific red, this specific green, and this specific blue. They also chose a particular white as their reference. These 3 hues, at their defined saturation levels, form the points of a triangle. By using these 3 colors in various combinations, we can recreate on television any color which falls within that triangle. Of course, it would have been nice to have a larger triangle, but producing phosphors that emit more saturated light got into other problems that just weren't worth the trade-offs. These 3 colors, then, are called the primary colors. Let's experiment a bit. You already know that when we mix 2 colors of light, we usually get a 3rd color. For example, when we mix green light and red light, our eyes see neither green nor red, but yellow. Now let's go one step further. If we choose our proportions of red and green carefully, we can achieve a yellow which, when mixed with blue, will give us white. This blue and this yellow, then, are said to be complementary. Likewise, red, when mixed in proper proportions with a color called cyan, are also complementary. That is, they make white. Cyan is made by mixing blue light and green light. And the complement to green is called magenta, which is a mix of red and blue. Anyone who's ever seen the standard color bar chart will recognize all 6 colors. The primaries, green, red, and blue, and their complementary colors, yellow, cyan, and magenta. Now, how do we make sense out of hue, saturation, primary, and complementary colors when we apply them to television? Let's begin with the television camera. For our purposes, we'll use a camera with 3 pickup tubes. There are other kinds, but the 3-tube camera shows the concepts best. An image passing through the lens first encounters an optical divider, which splits it up into 3 partial images, one containing all the red light in the image, one with all the green light, and the 3rd with all the blue light. Each partial image is then projected onto the face of a pickup tube. These tubes are all essentially the same, only the fact that they're receiving just one hue of light defines them as the red tube, the green tube, or the blue tube. Their jobs are identical: to transform the light they receive into an electrical signal, which varies in amplitude with the intensity of the light striking the tube. Incidentally, the signals coming from the tubes are indistinguishable, but we've colored them in here just to help us keep track of them. Our first task is to combine portions of these 3 signals into a single monochrome signal, which we call luminance, or Y. This signal is essentially a complete black and white picture. And if we were to transmit Y as it stands, any receiver, whether black and white or color, would reproduce this signal as a black and white picture. But we now want to transmit the color information as well without interfering with the black and white picture. Now this is where it started getting tough for those original designers. Whatever color information was to be sent had to fit into that same tight 4.2 megahertz space used by the monochrome signal. No more space was allowed. Right away, that left out transmitting red, green, and blue as 3 independent signals. The challenge was enormous. Somehow, the 3 color signals had to be pared down to fit into the limited bandwidth, again without interfering with the black and white picture. The first step, ingenious in its conceptual simplicity, reduced the color signals from 3 to 2. Here's what happened. Recall for a moment that we said mixing all 3 primary colors gave us white. It makes sense then that if we start with white and subtract any 2 of the primaries, we're left with the third. Subtract red from white and you get cyan. Subtract green from cyan and you get blue. Therefore, if we're already transmitting a luminance or black and white picture to the home receiver, we only need to transmit 2 of the primary hues and let the receiver recover the third. The next question was, which 2 primaries do we send? Well, we know that green has the most visual impact. Distortion in the green signal will be much more apparent to the viewer than a distorted red or blue. So the choice was really quite simple. Make the green signal the primary component of luminance, Y, and send it through the hi-fi part of the video band. And in fact, nearly 2/3 of luminance comes from the green signal. In this way, both green and luminance maintain their clarity. That leaves red and blue to send as the color signals through the chrominance or lo-fi part of the band. Next, after combining the 3 signals to get Y, we then subtract Y from the red and the blue color signals. The results, R minus Y and B minus Y, are called the color difference signals. We do this so that when there is no color information needed, the 2 chrominance signals will be 0. But some of you may ask, what about I and Q? A valid question. So far, our chrominance information consists of 2 voltages or amplitude signals, R minus Y and B minus Y, which we could choose to transmit as is. But doing so would give us colors in the receiver that are not exactly true. Here's why. Let's represent B minus Y as a straight horizontal line. Better yet, let's make it an axis. Next, let's make R minus Y the vertical axis. Now we can have both positive and negative values for the B minus Y and R minus Y voltages. You can see that by using this coordinate system, we can pair up values of R minus Y and B minus Y, whether positive or negative, to locate any point on the grid. Let's pick a color, cyan for example. To send cyan, we must give B minus Y this value and R minus Y this value. And by locating our coordinates, we can find cyan represented here. Actually, any combination of B minus Y and R minus Y which falls on this line will be cyan. Thus, specific sets of paired voltages can be said to represent a particular hue. In fact, we can create virtually any color within the system's limits by pairing values of R minus Y and B minus Y. That's clear enough. But here's the hitch. The eye does not respond uniformly to all these colors. Remember, we see color detail best in the red-orange range. It would be a real advantage, they decided, to have one of the axes pass right through the center of that red-orange area to which the eye is so sensitive. So they rotated the axes 33 degrees. The axis passing through red-orange became the eye axis, standing for in phase. The other axis, forming the quadrature with I, was thus labeled Q. Both the RY, BY, and IQ methods do the same thing. Paired voltages represent certain colors. The only difference between the two at this point is their relative positions. Let's return to our transmission chain where we find that we have three signals to transmit: our monochrome or Y picture information, and now our two shifted chrominance signals, I and Q. It would be nice if we could now modulate and transmit our two chrominance amplitude signals side by side on different carrier frequencies. Nice, but not possible. There is still too much signal for that 4.2 megahertz band spread. Back to the drawing board. If only they could combine the two chrominance signals somehow so that they would fit in with the monochrome signal, they felt that they could jam them all into that band without unnecessary interference. Now, they already had one carrier wave modulated by the luminance signal. But here's where it became a whole new ball game. They generated a second carrier wave and modulated it with one of the chrominance signals. Then they took another carrier from that same oscillator, but 90 degrees out of phase with the first, and modulated it with the other chrominance signal. The result was two separate signals, one containing the I information, the other containing the Q information, using carriers at the same frequency, but 90 degrees out of phase with each other. In doing so, they found that they could transmit both color signals within the same bandwidth as the luminance signal. Well, why not do the same thing using R minus Y and B minus Y instead of going through all that axis shifting business? And again, the problem lay in that crowded 4.2 megahertz bandwidth. If we were to use R minus Y and B minus Y and keep good color definition, we'd have to give each a bandwidth of about 1.5 megahertz. Well, this was unacceptable because of the interference it would cause with the luminance signal. But by rotating the axes to I and Q, we could use the full 1.5 megahertz we needed in that critical red-orange range while limiting the other channel to only 0.5 megahertz. Remember, the eye is less sensitive here, and not lose any color definition. And again, the interference between luminance and chrominance was held to acceptable limits. Unfortunately, for all the advantage of better color, there was a major drawback. The complex electronics required to use I with 1.5 megahertz and Q with only 0.5 megahertz made the system much more expensive than the RY-BY system. So you'll find that for all transmission and some special high-quality receiver applications where accurate color is essential, the more expensive I and Q are used. But most receivers still demodulate RY-BY for economic reasons, at the small sacrifice in color definition. Actually, most viewers are little the wiser. Next, let's turn our attention to the way we mix the color information with the monochrome signal for transmission. When we say that the monochrome signal occupies a 4.2 megahertz bandwidth, we don't mean that it occupies every single portion of that spectrum. Actually, clusters of energy appear every 15,734 hertz. Each cluster is an harmonic of the basic scan rate or picture line rate and contains a number of tightly packed sidebands of video information. But the space in between these sideband clusters is relatively empty. This seemed like the ideal place to put the color sidebands, the signals containing the I and Q information. One of the carrier frequencies whose sidebands will appear in these spaces is 3.58 megahertz. Sound familiar? Well, that's exactly why it was chosen to be the color subcarrier. Now, both the monochrome information and the color information can be shuffled together and sent simultaneously without too much interference. This shuffling process is called interleaving. And the result is a 4.2 megahertz video band containing the black and white picture and the two picture coloring signals. The combined monochrome and color information then goes to the transmitter, along with the audio, of course, and is spewed out all over the city. So how do we now decode all that information in the home receiver and make it into a real picture again? For our purposes, we'll skip what happens in the tuner and detector stages, the audio circuits, and so on, and just work with the composite video signal. Here it is coming out of the detector, carrying both black and white and color information. First, let's split out the monochrome picture or Y signal and put it aside. We'll use it later to build up a color picture. Naturally, if you have a black and white receiver, it has all it needs in the Y signal to reproduce the picture and ignores any other signals. In the color set, however, before we can make use of the color signals, we have to recover them from the modulated carriers. Remember now that even though the transmitter sent us I and Q, we have just an ordinary home receiver, and to keep the cost down, we'll demodulate RY, BY. One demodulator recovers the B minus Y information by comparing it to a 3.58 megahertz reference generated by an oscillator in the receiver, one just like the oscillator in the transmission chain. The other demodulator then must recover the R minus Y signal. It compares the other subcarrier to the same internally generated 3.58 megahertz reference, but shifted 90 degrees. To demodulate these signals correctly, however, that reference oscillator must be oriented exactly the same as the one in the transmission chain. This is done by locking the receiver's oscillator to the transmission oscillator. And that locking function is the sole purpose of a signal called the color burst. Here's how it works. Let's go back to our RY-BY axes. We know that a signal on the B minus Y axis will have some value for B minus Y, but R minus Y will be 0. We've already used our 0 degree position for the B minus Y signal and our 90 degree position for the R minus Y signal. But if we continue around the grid to the 180 degree position, we find ourselves right back on the B minus Y axis again. So let's use the 180 degree tap of the 3.58 megahertz encoding oscillator as our reference point and call it the color burst. We'll transmit that to the receiver's oscillator so it can lock itself to the encoding oscillator, making sure the axes are oriented properly. Of course, we don't want the burst to interfere with our 3.58 megahertz color subcarrier, so we'll send it out when there is no color information being sent, say at the beginning of each scan line. Now, before the beam scans each line, the receiver's oscillator checks itself. If it finds that the burst has a positive or negative value for R minus Y, it knows that it's out of alignment and shifts itself so R minus Y is 0 again. Now that the axes are straight, the beams begin their trip across the screen. In this way, correct color demodulation is maintained line by line. We now have two properly demodulated color amplitude signals, which will determine the coloring of our picture. Next, we must reconstruct our green difference signal by adding about 1/2 of the R minus Y signal and about 1/5 of the B minus Y signal. Now that we have three color difference signals again, R minus Y, B minus Y, and the derived G minus Y, all we need to do to get our original colors is add Y, which we sent over earlier. And there they are, our original red, blue, and green signals, nearly the way they came out of the camera pickup tubes. It should be obvious that if there is no color information sent, R minus Y, G minus Y, and B minus Y disappear, and the picture tube will display only Y information, or a complete uncontaminated black and white picture. Now that we have our red, green, and blue picture signals back again, the remaining job of assembling our original image falls to the picture tube. Like the color camera, there are many ways to recreate a picture in a color tube. For our illustration, we'll use this Sony Trinitron tube, the kind used in Tektronix color picture monitors. Instead of one cathode and one electron beam, as in a black and white tube, we have three, side by side, one for each color. And in place of a single phosphor coating on the screen that produces a single color of gray, we now have hundreds of tiny vertical color phosphor stripes, red, green, blue, and so on across the entire screen. The electron beam carrying red information strikes the red vertical stripes as it scans the screen horizontally. The green beam scans the green stripes, and the blue beam takes care of the blue stripes, causing the phosphors to light up in proportion to the beam strength. But how does the red beam know to hit just the red stripes, and the green beam just the green stripes, the blue beam just the blue stripes? Well, here's a representation of a picture tube as seen from the top. Here are our 3 cathodes and just 3 of the hundreds of vertical phosphor stripes as seen on end. And this is called an aperture grill, a metallic screen with 1 vertical slit for each of 3 colored phosphor stripes. You can see that the aperture grill allows the red beam to strike only the red stripes, the blue beam only the blue stripes, and the green beam only the green stripes. And with that, we have, once again, a complete color picture. Of course, if the picture is black and white, all 3 guns are locked together, and the mix of red, green, and blue light emitted by the phosphors produces what our eyes and brain perceive as varying shades of gray. Well, that's the basics of color video, but before we close, let's clear up some loose ends, like vectorscopes. As we've made clear, vectors as such are not transmitted, just varying values of 2 chrominance signals 90 degrees out of phase. And here they are, I and Q. Now, if a television engineer wanted to evaluate these constantly changing values, it would be difficult to say the least. So the vectorscope takes each set of I and Q values and displays it as if it were a vector. Here's our standard color bar chart, for example. Red is transmitted as 2 specific I and Q values. The vectorscope takes those 2 values, creates the resultant, and displays it as if it were a vector, complete with phase and amplitude. The red vector has a phase of 103 degrees. Each of the other color bars also has a specific phase angle and amplitude on a vectorscope. And with this standard test signal, we can check the accuracy of our system. Each of the 6 value pairs for primary and complementary colors, as represented by a vector, should fall within the boxes provided on the graticule. In this way, the video engineer can tell at a glance if the color signals he's sending are properly aligned. Another important signal for the vectorscope to display is the color burst. Remember, the burst should fall on the 180-degree axis. Now look what happens to the colors if the burst strays. The demodulators in the receiver shift with the burst, and the result is that the wrong color information is sent to the picture tube. The vectorscope then lets us verify at a glance that the burst-color relationship is correct also. The vectorscope is an invaluable tool in any color television system. One final point will wrap up our introduction to the basics of color video. The system we've illustrated is that defined by the National Television Systems Committee, or NTSC. This system is mainly found in the United States, Canada, and Japan. There are others: CCAM, developed by the French and used as well by the Russians, and PAL, found in England and the European mainland. Conceptually, they're much the same, but differ in things like how the chrominance is modulated. Now, let's run it back to the beginning and review some of the concepts we'd like you to remember. Color video relies on 3 primary colors: red, green, and blue. By combining them in different proportions, we can recreate almost any color to which the human eye is sensitive. Now, color has 2 properties: hue, or which color it is, and saturation, or how much color there is, how much the pure color is diluted by white. There's a distinct difference between saturation and brightness. Where saturation refers to the relative amounts of color and white in percent and represented on a waveform monitor as the peak-to-peak value of the band, brightness refers to the intensity of the composite signal in IRE units and is represented as the average value of the band. A complementary color is one that, when mixed with its paired primary color, gives us white. The complement to red is cyan, the complement to blue is yellow, and the complement to green is magenta, and so on and so on. In the television camera, the image is split into the three primary colors, which are in turn projected onto the pickup tubes. Each tube converts its light image into an electrical signal. Portions of the three signals are then recombined to give us our monochrome picture. The primary component of the luminance signal, or Y, comes from the green pickup tube. Y is then subtracted from the red and blue signals to form the color difference signals R minus Y and B minus Y. These signals are then rotated 33 degrees to form I and Q, which modulate the color subcarrier. The I signal, carrying the red-orange information, modulates one subcarrier and is given 1.5 megahertz bandwidth. The Q signal modulates the subcarrier taken from the same oscillator but 90 degrees out of phase and is given only 0.5 megahertz bandwidth. In this way, the red-orange signals, to which the eye is most sensitive, are transmitted with more definition than the other colors. Along with the two color amplitude modulated subcarriers, a reference burst taken from the oscillator at 180 degrees is sent at the beginning of each line to lock the receiver's oscillator to the encoding oscillator. The chrominance signals, based on a 3.58 megahertz subcarrier, are then dropped in between the monochrome signals in a process called interleaving. In the receiver, the process is reversed. Composite video is divided into the monochrome signal and the two color difference signals. Two demodulators retrieve the color amplitude signals using R minus Y, B minus Y axes instead of I and Q for most sets to keep the cost down. The two independent R minus Y and B minus Y signals are then used to derive the missing G minus Y signal. These three are then sent to the picture tube circuits where they are reunited with Y. The Sony Trinitron striped picture tube uses 3 electron beams, one for each primary color. By using an aperture grill, each beam scans a corresponding set of vertical phosphor stripes that glow in proportion to the beam's strength. And the result is a clear, crisp, brilliant picture in beautiful living color. Well, that's it for the basics. And now, while you ponder your new frontiers of knowledge about color video concepts, we'll fade to black.
Yeah.